Hey there, how's it going? Terry Brown, Mechanical Engineering here with another solution to engineering mechanics problem. So this time it's just a simple moment of a force type problem. So let's get into it. Right, so here's the problem. Typical kind of textbook problem, really just the kind of problem to help you develop your skills and understanding of what the moment of a force is and how you go about calculating it for different applications and different contexts. So here we have here at the top right of the little picture, the 50 Newton force acting at 60 degrees to this bent pipe assembly. And we want to know what the moment of this force is about the point O down here at the bottom left-hand corner. Right, so redrawing the problem. So it's a good idea to get into a habit of drawing your diagrams, get used to drawing things nice, neat and clear, so that you can easily see what's going on. And just taking a little bit of time to do this helps you to think about the problem as you're going about it. And take the time to do it roughly to scale. It doesn't have to be not so much roughly, but approximately to scale, so that you can then use that in assessing whether you got your calculations right. And I'll use it to check my first calculation here. So I'm going to look at this, solving this in 3 different ways, or 2.5 ways really. So looking at this, I think most of you would probably say, oh, the easiest way to do this problem would be to break this force up into horizontal and vertical components, and then find the perpendicular distances for each of those components. And yes, I would agree. That to me is the easiest way to do it. So you probably know that that's called Varignon's theorem, or the principle of moments. And I like to write the equation for Varignon's theorem, or the principle of moments, like you can see on the screen here. So the moment is equal to the sum of the moments of each of the components. So typically we'll have components in x and y directions. They don't have to be, but usually that's the case. And you can adapt this equation to, or this formula, to other coordinate systems and other directions of components, if you like. So we have the force in the x or horizontal direction times the perpendicular distance, which will be in the y direction if we're in the forces in the x direction. And we need to look at the moment that's generated by this force to determine whether it's positive or negative. And of course, we'll need to indicate here what we're considering to be positive or negative, and we'll do that in a second. Then we'll also have the vertical component of the force times its perpendicular distance to the point about which we want to know the moments. Right, so let's put in our horizontal component up here. So this one here, and consider that little right angle triangle there. We can see that this bottom side here, where we've drawn our component, is the adjacent side to the 60 degrees corner. So therefore that's going to be 50 cos 60 degrees for that component. Similarly for the vertical component, and again draw the force components at their proper line of action. Right? So it makes it obvious where, or obvious what the perpendicular distances are. Don't draw it out here, but we know obviously that the length of this component will be the length of this side of this triangle. So that's the opposite side of this little right-angled triangle. So that we know will be 50 sine 60 degrees. Now we need to work out our perpendicular distances. So if we here continue our line of action of this horizontal force component Fx, continuous line of action, and then we draw a line from the point that we want to take moments about perpendicular to the line of action of the force. As I've said in other videos where I go through the calculation of the moment of a force, it's important that you know and understand the full definition of what a moment is. Okay, so a lot of people just remember force times distance, or even force times perpendicular distance. But to be able to apply it consistently and correctly all the time, know the rest of the sentence about what the moment is, and it's the perpendicular distance from the point that we're calculating moments about, perpendicular to the line of action of the force. So in this case, it's this distance here, dy, and right, so I'm just using this little triangle here, right? So we can see that this vertical side here will be opposite to the 45-degree angle here, so that there will be 200 sine 45. And then if we want to know the perpendicular distance to this vertical component here, right? So again, this is where having drawn my component at its correct line of action helps. So here I draw my line continuing through the line of action of this vertical component Fy, and then I say, okay, what's the distance perpendicular to this line of action from point O? Okay, so that will be this blue line that I've drawn here and labeled dx. Okay, so here, hopefully you can see that that is going to be 100 plus this 100 plus the bottom or the adjacent edge of this triangle adjacent to the 45 degrees. So let's put those numbers in. So for fx, we had 50 cos 60, and its perpendicular distance was 200 sine 45. So just the height of this little triangle that I drew before. So now we have the magnitude of the moment of this component force. Now we need to know whether we put plus or minus in front. And to do that, we need to indicate what we're considering to be a positive or a negative moment. So I pretty much always indicate anti-clockwise as positive for a moment, because usually x is positive to the right and y is positive upwards. So in that case, anti-clockwise is strictly correct for the moment. Okay, so here we have this force here, 50 cos 60 times dy, and that will tend to rotate anti-clockwise, right? And as I often say, if you're not sure, right, just get your pen or ruler or whatever it is, put it on your page and push in the direction of the force. I'm not sure again which way I'm looking relative to the object that we're analyzing back on the other page, right? But you get the idea, right? Just hold it where you're calculating moments about. So this down here will be point O, and then just push in the direction to see whether it goes clockwise or anti-clockwise. Okay, so here we are back at our problem, and so we can put in a plus at the front of this one, or you can just leave it out. Doesn't matter if you don't write plus there, right? As long as you don't write negative if you've got anti-clockwise as defined as positive. So the next one is our vertical component. So the 50 sine 60 that we've got here, and as we discussed before, we've got this 100 plus this 100. So that's how we've got 2 times 100 here, plus the adjacent edge of this little right angle triangle here where the hypotenuse is 200. So that will be 200 cos 45. Is it clockwise or anti-clockwise? So if we look up here, this is pushing downwards out to the right of point O. So hopefully you can see that that will tend to rotate around this way, around clockwise. So therefore, this one is going to be a negative moment. So put minus sign in front of that. Okay, so now that we've done that, we've found the moment effect of each of the components. Just do our maths and we get minus 11,248 Newton millimeters, and we see that that's negative, so that indicates that the moment is clockwise, and in this problem you can pretty much see that that's going to be the case. Now we just need to convert to Newton meters, so just divide by 1,000, because there's 1,000 millimeters in a meter, so that just becomes 11.2 Newton meters clockwise for our moment. Let's now have a look at method 2, and what we're going to do here now is to find the perpendicular distance to the line of action of the original 50 Newton force that's acting at 60 degrees. I'm not going to go through the detailed trigonometry and geometry to work out exactly what the perpendicular distance is. I'm just going to make an approximation to do this as kind of a check on my calculations from Varignon's theorem. All right, so here just continue the line of action of the force down here. So our 50 Newton force is acting at 60 degrees to the horizontal. Line of action comes down here. And then our moment, our definition of a moment is the force times the perpendicular distance from point we want to calculate the moment's about to the line of action of the force. Okay, and this distance is perpendicular to the line of action of the force. All right, so we could go and do some trigonometry and geometry and work out exactly what this value is. I'm not going to do that in this video, but I can see, right, just by looking at this, that it's going to be approximately 200 millimeters, thereabouts, maybe a little bit more. Okay, so if that's the case, if we approximate, so this is an approximation, not an equals. Right? So we're just saying it looks roughly 200 millimeters. Right? And this only works if you've drawn your diagram reasonably to scale, right, or approximately to scale. So 200 times 50, so that's that 10 Newton meters, approximately, right? So our answer that we got before was 11.2. So looks like we got this right. Like we haven't messed up a sign here, right, for example. You haven't got minus here and plus here when we shouldn't have, and so on. So just give us a quick check on our calculations. And we can also see that, right, obviously from this, that the moment about point O is clockwise. So let's go to, before we go on to the next method, just want to quickly note that these values dx and dy that I calculated up here, right, they are not the components of this distance d here. Okay, so don't make that mistake. Okay. This dx here and this dy, they are not the components of this distance here d. All right, so let's go to the next method. The method I'm going to use here is the vector method, so using the vector equation for moments, and hopefully you remember that that's r cross f. So r is our position vector and f is our force vector. So we need to indicate what they are. So the position vector, or the distance vector, is from the point that we're taking moments about to somewhere on the line of action of the force. Right, so this could be anywhere, right? So we could continue the line of action of this force down here, work out this distance here to, or the position vector to that location, and do the calculation that way. But we've already been given all of these dimensions here, so it makes sense to do our position vector 0 to this point here that we know about. All right, so indicating our coordinate system, x and y. So r will be in the horizontal direction. So essentially what we're doing is finding the components of this position vector, right? So, you know, it's much the same as doing the Varignon's theorem that we did before, but we're, you know, using vector notation. Right, so this term here, right, is the x component of this position vector r. So I just need to know how far this is going in the x direction. So as we saw before, it's 2 times these hundreds plus 200 cos 45. And then in the vertical direction, the j direction, right, what's this distance here? Just 200 sine 45 that we saw before. Okay, multiplied by the unit vector j. Okay, so that's our position vector. Then our force vector, Again, right, you can see this is essentially just finding the components of the force, right, and just putting I and J next to them. Okay, so here we have, well, the horizontal one is 50 cos 60 going in the negative direction. Okay. So it's a negative vector in the I or X direction, and then the force, the Y component acting downwards, 50 sine 60 as we saw before, times J, and it's in the minus on the negative direction, so we've got a minus sign out the front. Okay, so now that we have that, we've just got to do our cross product. Just reminding you that I cross I equals 0, J cross J equals 0, I cross J equals positive K, and J cross I equals negative K. So if we do our cross product, so there's a number of different ways of doing that. I like to just multiply out for small problems like this. If you have a large vector, larger vector and matrices that you need to do the cross product for, you can use other methods. We're not going to worry about the I cross I's and the J cross K's. We know that they're 0. We're just going to worry about the I cross J. So we take the first term, 2 times 100 plus 200 cos 45 I times sine 60 or minus sine 60 J. So I cross J gives us K. So that's where this comes from. And also because I got 50 in front of both of these terms here, I've just taken the 50 out the front. Okay, so then the next one, J cross I, so it'll be 200 sine 45 down here times minus cos 60, and J cross I gives us minus K. Multiply all that out, we get minus 11,248 K Newton millimeters. Okay, and we get the negative sign out the front here as we got before. So assuming that you get your vectors right here and you do your cross products correct, then the signs of the moments are taken care of by the vector cross product. So here where we've got J cross I, this is where we get a minus K. Right? So that's how that's dealt with or taken care of. So we just rounded, we have rounded this to 3 significant figures and converted it to Newton meters. And just a reminder that the actual vector, because it's K direction, right, the vector is actually along the Z axis. And using our right hand rule, we can see looking down the Z axis at the XY axes, that's a clockwise rotation. Okay. About the Z axis if we're looking down the Z axis at the X and Y axes. All right, so that's the end of the problem. All right, hopefully that was helpful and informative for you, and good luck with your problem solving. Catch you in the next video. Bye for now.